You're live.
All right. Welcome to the Collins Amateur Radio Club. What? It's not working?
Got you on the camera.
You don't. Oh, over there, that thing is not very loud, and they got a big deal about messing with the knobs. So I suppose we'll first go around and introduce everybody. I'm Charlie, KC0CD.
Rob, 80EH. Terry, KE0RBX.
Dan Johnson, WV5LCO.
Larry, A0M10.
Dave, WA9HBC.
Gary, K0G2.
Jim, W0NN.
Al, WA0JYM.
Bill, N0LNO.
Christopher, KC0YGW.
Joe, WB0YFL.
I'm Ron, K0DAS.
Larry, K9HHK.
Bob, KW0.
Larry, WA80FDH.
Tim, KC0DF.
Mike, KC0PB. And Vince, N2AIE. And Barry.
All right. And there's Barry. All right. So the treasurer's here. Give us a report on how much is left.
Oh, I don't hear that right away, okay. Sure, nothing, no. The total,
Being a sound mind, I spin it all.
the total is 11,134.19, split between the savings and the,
Yeah. Okay. 11,000. Oh.
keep enough in checking so we can cover anything.
All right. We'll get to that other. What can be done around the stations? The annual sign-up dinner normally happens in September. Last year we tried the Long Branch and ended up with 2 great big trays of potatoes, mashed potatoes and cauliflower and meat and everything. So the number, I mean, you have to pick a number before with them. So you end up writing a pretty big check, and we had just a handful of folks come. So I thought something a little bit more adjustable might be the better. There are a couple of Chinese place cafeterias, but the Pizza Ranch over in the west side, they have 2 rooms they can open up, so you can take about 70 folk, so you can bring your spouse. $13.25 if you're less than 60, $11.76 if you're over 60. Or we can do what we did a couple of years ago, is just order some pizza into the new main plant cafeteria, because it's a lot nicer than it used to be. So, what's everybody's feeling, ideas, thoughts?
I like the parking of the main plant idea.
How good pizza did
Well, what kind of pizza did we get?
What, last time we had it?
Yeah.
A little bit of everything. We ordered a mishmash.
From,
Domino's?
Oh, where did we get it from?
yeah.
Oh, now you're gonna have to do a couple of things. Hell, man, it's right out.
Godfather's was only 8 blocks away or something, so we had to go over there. That's not a long.
Okay.
Godfather's has a back room.
Oh, if you want to do it there. Oh, yeah, that's true, they do. I don't know how big it is, but that would be a possibility. So you want to go on?
Pizza Ranch, are we able to adjust the number of pizzas sort of as people come in?
Oh, yeah. Yeah. No, it's a buffet. So that's a flat rate. Everybody that comes to the door pays that amount, and then they have chicken and beef and mashed potatoes and pizza.
Yeah. So if we go to the main plant, we're going to pre-order and we're going to be stuck with whatever we get. But
Right.
we can probably,
Is that what the feeling? We want to give the pizza a shot?
Let's do a vote.
Let's do a vote. How many want pizza?
Well, you
What? Oh, you want to make it official? Oh.
saying, I want pizza not at Rockwell Collins.
Or pizza-
Or pizza at Rockwell Collins.
Well, if it's at Rockwell Collins, there won't be a choice for the chicken and the beef and the mashed potatoes.
But asking if you want pizza.
Oh, well,
It's
okay.
not clear. It's not clear.
You're right. Okay, pizza at main plant. How many for pizza at main plant? Raise your hand. Okay, 1, 2, 3, 4, 5. 5. How many for pizza at Pizza Ranch? That's a majority. Okay, we'll do pizza. We'll give Pizza Ranch a try. I will make, as we get a little closer, I'll make a reservation over there for their back room, and then you just get what you want. All right? Okay. Next that will be, now the other question is, do we have it on the usual Tuesday, the 11th, or do we have it right before the CVARC meeting, which we've done the last couple of years? Because then you go to dinner, and then, I mean, you kind of dedicate the whole evening to the ham radio type thing. Have dinner, and then you go, because we'll start at 4:45 or 5, something like that over there. And you hopefully, I mean, you continue to eat if you want all evening. You can sit there and just keep hammering it in. But, but most of us would go over to the CVARC meeting then. When's the CVARC meeting now? Is it 7? 7, okay. So yeah, you got enough time there to get a few chicken wings put away and a few pieces of pizza. So what's the preference?
I'm gonna be in New Zealand, so I got a business trip.
Down with the Kiwis, huh? All right. So what do you think before they see Thursday? Is that good?
Thursday's great.
Okay, we'll have it Thursday before the meeting. Good. Come in. You can join the meeting if you want. This is the Amateur Radio Club.
Down, we're waiting for you.
Yeah.
You should have waved at the camera when you walked by.
Yeah. Okay, so we have some changes coming down. Dan is stepping down. He can't just handle the stress of all that money. So we need somebody to step up and be the treasurer. And so contact me if you'd like to help out on that. That'd be super. Also, if we had somebody that could do programs, that would be really nice, because it's kind of falls in my lap to try to find somebody every 3 months. And so that's kind of frustrating. Okay, this is the same slide we had last time, but just want to announce that it's up, it's running, it's down at main plant, has the latest software in it, and it's fun. It's a new way to do it, and of course we have all the other kind of things down there, all the other kind of radios also. So if you want to get checked out, talk to me, and I'll give you a check out on the thing, and you can use it. And then Midwest Convention, August 4th and 5th. And one of the things they've asked us to do is to do the club to do something, and I volunteered to set up the KWM2. Thought that'd be easier than trying to set up the S-line or something with more than one piece. At least that's kind of a standalone unit. So anybody have any other suggestions? We're trying to set up some tours. What's that?
Did you include my slides I sent today?
No, I didn't see them.
Okay. So I had suggested that,
Okay.
we set up a classic Collins station. That's what we talked about.
That classic enough?
KWM2.
Okay.
And we just, we need people to set up the antenna and stuff like that. So I was just wondering who, wanted to do it. I'm kind of interested in operating and doing that during the Ham Fest. So.
Oh, I will be here. I'll probably be giving tours of the museum.
So are we going to do that for sure?
Well, some folks are pushing for it.
That was on my list because I haven't heard if it's positive or negative.
Well, we haven't figured out whether or how much hassle it's going to be to get people on campus. My understanding is that they can sign in at the guard station as long as it's before 4 o'clock. We can get them a museum tour. Now, I don't know if that means we can use the same badges to get them into main plant for a station tour.
We're working on that. The CCA wants to come in Friday afternoon. They're gonna be in the Long Branch about 2 o'clock. And then they're going to plan to be at the museum about 3. So far, I haven't got any good response from security and how we handle all this. But
Right.
we have told them they have to have all their information in by not later than August 1st. And so, because we got to take that list in 24 hours in advance for this action.
Well, if we have to put them in the safe system.
Yeah, so I don't know anything about the safe system, so I'm.
Yeah. Well, you just need somebody that knows how to enter their names and we can get their badges.
And then we'd hope we could then say do a 3 o'clock for about an hour at the museum. And
Christopher.
then head down to the main plant about 4:30. And try to get into the main plant pump station down there. So
Yeah.
now we do have a table reserved for the club at the Ham Fest. And then there's a College Collectors Association club line. It's right in that main hallway, just posted in a wearable booth, so it's easy to track.
So, will there be a table somewhere else for the classic?
That's the only table I've got, just the one for the College Collectors and then the CCA and then the College.
Yeah.
So I was gonna suggest that we do it outside in a tent, probably in some open area. I don't know, Tim's not here, is it?
Well, they're going to have the big white freezer tent. The EMA tent's going to be set up.
Oh, we're gonna set that up? That comes with power and AC.
Yep.
We've been there for field day, it was beautiful. So, this is the first I've heard this. So, is this an absolute positive?
I believe it is. Yeah, last time I went.
What's the plan for that tent to be set up for and why?
It's forums and for workshops.
So it was for forums and workshops in the tent?
No, I thought there are going to be several stations set up. But yeah, we'll have to check on that. So at this point, we'll plan at least on having this. I think we may be able to snag some parts out of some of the rigs out of the museum club to have an actual setup. You know, with the W0 CXX and some of the old equipment. Right. Maybe haul one of the.
I'm gonna take that after the tour down there if we have it.
Yeah.
Set it up.
Now, if we got a forklift, we can bring ART-13, you know, to sit out there.
Well, we had a banquet Friday night at the Long Branch that's going to sort of commemorate
Oh!
the KDM 380 introduction in 1979 to the dealers.
Yes.
Dave Burr's going to be the speaker, and then Rod and Kenny Day and Jim McConney are supposed to show up.
Oh, okay.
We think that there's probably 8 or 10 people in town that are interested in hearing the 380 story, so we think we'll have that. So they expect 35 in from around the country for the banquet. How many we have for the tours, we don't know. 10, 15, 20 probably.
So I should refresh my membership of the CCA, huh?
Yeah.
There you go. All right.
Have a table.
All right. So we also, this is the same slide we had last time. We have on loan a 6700 that can be remoted into, and I've done that. It works really slick. So it comes up real fast because it's already turned on. It comes up faster than a 6700. You just click on it and up she comes, and you can check the bands and everything's going, and they have 2 antennas crossed. The other night I was on there on 20, listening to a guy, and so I put it in the diversity mode. So that puts antenna 1 on one slice and antenna 2 on a second slice, and so it comes out the speakers separately. Antenna 2 is coming out the right speaker and antenna 1 is coming out the left speaker. You can hear it move back and forth, you know, this guy will get weak and this guy will get low, kind of a stereo weird effect. So if you want to get checked out on that, talk to me and I'll get you the passwords and all that good stuff to get on there. I think in the last 6 months there's only been once when somebody else was using it. So it's not used that much, yes. It's located out at, oh, he's got it up right now. Right there on the phone. So it's north, what is it? So it's, you know, it's not in town, so it's noisy. It's less noisy than what we have over here at the station. Okay, and so we've got the whisper and the radio's up. You can come and use the station. If anybody hasn't been checked out on the equipment, you know, let me know. I'll check you out on all the radios that you want to run. And there's some things that could be done at N0CXX. Be nice to get that 100 watt, 160 watt amp for the 2 meter. So when we get some rovers going here, we can talk with them from there. And over at main plant, the big thing is we've got the 9100 does HF, VHF, and UHF, so you can do that terrestrial stuff right now. We've got that hooked up. We do need a little bit of work on the satellite operation. So anybody that wants to pick that one up certainly can. And that's just about it. Set up the satellite station. So that's about all we have for this. Now, I'm going to switch over to talk about how to build a filter. Let me bring up his PowerPoint.
Charlie,
Yes.
on one of your previous slides, you talked about the 6600 being remote control.
Well, what I meant by that is it can run on the computer in that room. So you can run it so it looks like all the flex displays. I've got two displays that will come up on the two computers. So you could have it on 2 different computers. We can't remote into it because we don't have an internet on it. You got DSL down there that has the speed of about 10 hertz. Yeah, this is the speaker for the room, but it's just not working. This one here is the video.
The recording.
So, you know, we installed a printer on 12. The 3D printer. And it seemed like nobody was using it. So I brought it over to my building and it's hooked up to the network. So if you have something to print, you can remote into a PC and then just let me know and I'll turn the printer on so you can print it. It seemed like a better way to have access to the printer. Budget doses, or you're the expert. Cranking out bezels for displays. Sorted pieces, if you want to use PCB boards for case, print corner pieces, just slide the PCB boards in there. That's kind of cool.
Okay.
Ready?
All yours.
Okay. Well, this was presented in 2009 up in the 166 upstairs. Some of you may remember that. And it covers a smattering of things that baffled me at times when I was learning filters. And it isn't comprehensive by any means, and it does require some advanced knowledge of steady state AC analysis with the J omega complex numbers. Anyway, lumped element ladder filters. They're ladder filters because of the shape of the schematic. Looks like a ladder. Topics are going to be how filters work, and then a touch on L-match antenna tuners, which is kind of a filter, and then a brief introduction of low-pass prototypes, and then frequency and impedance scaling, which you need for making useful filters from the low-pass prototypes. And then there's an example of making a low-pass filter. Filters are mostly used to remove unwanted signals based on the signal frequency, and there's several types: low pass, high pass, band reject. There's also equalizers and probably a few others. The filters work by causing a frequency-dependent impedance mismatch between the source and load, and I want to demonstrate that here. Here's a Here's the source. The source ends right here at this point, and this is the load resistor. And power gets transferred from this source, the resistor and the voltage source, to the load resistor. And the quantity that transfers into the load resistor depends on the value of the load resistor. Here's a calculation of a 10-volt source and a 50-ohm load delivering power to a load resistor, and the bottom axis here is the load resistance value, and here's the wattage that gets into the load resistor. You can see it peaks out here at 50 ohms, and that's what the value of the source resistor is. And in fact, it's a half a watt, and there's a little formula that gets used a lot. It's the formula for the maximum available power from any source, and it's V squared over 4 times the source resistance. And in this case, you put the 10 volts in there and 50 ohms, and you get a half a watt. So that's the maximum you can extract from any source, is given by this formula. Now, the previous graph varied the load resistance, but you can also create a mismatch by having coils and capacitors in the circuit. The match condition then becomes a complex conjugate of the source and load, which is equal resistance and equal reactance, but opposite signs. And there such a thing is ideal. Well, the ideal capacitor and coil are described by Z equals Jx, where J is the square root of -1. And you've seen these formulas, I'm sure. This is for coils. The impedance of a coil is an imaginary 2 pi FL, frequency, inductance. And for a capacitor, it's -1 or minus J over 2 pi frequency times the capacitance. And Z is similar to a resistance, but it's an imaginary number, and it does not combine with the real numbers. And that's critical on understanding how these filters work. So here's a circuit where there's a 50 ohm source and a 50 ohm load, and there's two resistor, or a coil and a capacitor, ideal coil and capacitor in series in between the two. And again, this is the source part, this is the load, and here's what you would call a filter. And in this case, you can do a voltage divider formula and calculate the power in the load, and it turns out that at the bottom axis is now frequency instead of resistance. And it turns out that at about 16 hertz, I guess, you end up getting a half a watt. And that's the same old half a watt that we had on the resistive example. And again, the peak power, well, the frequency at which the peak power gets through is given by this formula here, which is dependent on the coil and capacitor value, but the maximum amount is half a watt. It's the same as the other one. And it's because the coil and capacitor reactance cancel each other out, and you're left with the 50 ohm source looking at the 50 ohm load, and you get the half a watt out. And note that there's no power loss because of those two parts. They're lossless parts. And that's because they're idealized. There's nothing but pure inductance and capacitance. So there's another, well, yeah, the gain of a filter or the loss of the filter is commonly described by what's called a transducer power gain. This is a stray sentence here. This is not the previous graph, but this concept here is power delivered to the load divided by the power available from the source. And this power available from the source is that little formula with the V squared over 4RS. This allows the easy evaluation of filter performance when the source and load resistances aren't equal. So now on to the L match, which is kind of a filter. A lot of antenna tuners use the L match, and the capability of the L match is that it will exactly match any two resistances at one single frequency, and the attenuation at other frequencies is not strongly considered, but it does attenuate. Components are in the shape of the circuit is in the shape of the schematic, I should say, is in the shape of the letter L. It's a ladder circuit, one series and one parallel element. It can be of a high pass or low pass variety, and it's typically used for antenna tuners. Cheapy antenna tuners, I would guess. Here's the formulas for designing an L match. This is the general formula here. Notice that this is plus minus and this is minus plus. These have to be opposite signs. These are either coil and capacitor or coil and capacitor. And here's a low pass example, coil and capacitor. And what you do, you plug in the source, the load, resistance, and you calculate this interim Q. And then from that, you calculate the reactance for the coil, or for the series element and the parallel element. And you can pick either coil or capacitor. They just have to be of opposite type. This is a low pass because you can tell because at extreme low frequencies, the coil reactance goes to 0, the capacitance goes to infinity, and you end up having the source resistance connected through a piece of wire to the load resistance, and there will be no loss at that point. It passes those frequencies readily. And at the high frequency extreme, the coil goes open circuit, the capacitor becomes a short circuit, and they disconnect, and so it attenuates a whole lot. And this is the low pass variety. And here's an example of a tuner that uses an L match inside. Now that little, I don't know if you noticed back, but the formula requires that one end of that L match be a higher impedance, higher resistance than the other. And you gotta wonder, how does that work in a tuner where where it will match resistances above 50 ohms and below 50 ohms? Well, the tuner has a set of relays in it that actually turns the L match around end for end, and so it'll match up or down from 50 ohms. And they have a microcontroller in here, which you've obviously, these are real popular now, but it does the tuning, and I think it's an iterative process rather than measuring of the impedance and then calculations. It makes a lot of clattering when you fire it up. So here's a frequency response of an L match in a low pass configuration. Notice at lower frequencies at this end of the chart, there's not much loss, and at the high frequency end, the loss is getting higher and higher. And the graph has two lines on it. One of them is just a magnified version of the other. This is 10 times the black line here, but it's a 50 to 500 ohm L match in low pass configuration. And then here's the same circuit. in the high pass configuration, and notice that at the high frequencies the attenuation's not very much, but at the low frequency end the attenuation is going up as you go lower. This is 10, 20, 30, 40 dB there, and up here it's like 4 or 5. So anyway, that's the difference between the two. One nice thing about the low pass version is that it will help attenuate your harmonics, because if you're operating at this frequency here, harmonics will be up here on the steep attenuation curve. Whereas on the high pass, you get no attenuation up here, essentially none. So if you have a choice, pick the low pass for your ham rig. Now I got a demonstration here about how an L match can match a one end of a filter to a stop band impedance and end up with no loss. It's similar to your antenna if it's off resonance. The L match can actually fix the off resonance problem and get a good match for you. In this case here, I got a filter which would be simulating your antenna, and I'm going to operate at this frequency, which is a mismatch. It's off frequency for the antenna. Notice the nice pass band here where there's no loss, 0 loss. But if we put an L match on one end of this, I can match this so that there's no loss here. And here's the case. I added 2 components, which is the L match, the same old filter, and notice at the marker frequency where the L match is designed, the loss goes clear up to 0. There's no loss, but it also destroyed the pass band, and it just proves that the L match can match any 2 resistances at one single frequency. So the filters with ideal coils and capacitors are lossless. That's what we've been dealing with here up to now. The real part of the impedance is the load resistance modified by the filter. Notice, I remember I said that the real parts and the imaginary parts don't mix in complex arithmetic, so any real part that shows up at the filter's input is a result of the load resistance. And if you remove the load resistance, the filter input impedance becomes completely imaginary and no power will go in. And then if you build a filter with non-ideal coils and capacitors, or essentially real coils and capacitors, each coil and capacitor has an equivalent internal resistance, and then that burns up some of the power from the source, and not all of the power gets to the load like it does in an ideal filter. And this is the characteristics. Filters with the ideal coils and capacitors, kind of an academic exercise. The output power equals the input power. When the input is matched, you get the most power transferred out of the source. And the higher the load resistance is, the higher that parameter QM becomes, and it causes a narrower bandwidth. And I'm sure you've all experienced that. Now, if you're using a real-world circuit with non-ideal coils and capacitors, the output power is less than the input power because some of the power burns up in the parts in the filter or tuner. Still, again, the one-to-one input match at the source still gives the most power transfer because it extracts the most power from the source. And also the same holds true with the QM factor. The narrower the bandwidth becomes with the higher QM. So something other than an L match to get into making an actual filter. You have filters with specified stop bands and pass bands. And you wonder, where do we get these? There's a process called network synthesis, which is a mathematical process where they generate the part values I'm not going to talk about that. Filters are generally conveyed to the end user by low-pass prototypes, which are circuits that have values that have essentially gigantic valued elements, like 1 Henry and 1 Farad. They're in that ballpark. A lot of different types of prototypes exist, and they all have their distinctive characteristics. And most are the same circuit, the same schematic, they just have different values. And they can have any number of elements. You can have cutoff frequency. Oh, they typically have a cutoff frequency of 1 radian per second, which is this number, 2 times pi times f. And they're scaled so that W equals 1 at the so-called cutoff frequency. They all have a load resistor of 1 ohm, and you can scale these to any impedance or cutoff frequency to make your own filters and customize them to what you want them to be. And you can also transform these low-pass prototypes into high-pass, band-pass, or band reject filters. And the transformed filters largely retain the characteristics of a low-pass prototype. Here's an example of a low-pass prototype. This is a 4-pole Chebyshev low-pass with a 1 dB passband ripple. And again, it's a lossless ladder circuit. The only resistors are the source and the load. And the series branches are these up here at the top, and the parallel branches are the ones that go to ground. And the values are in ohms, farads, and henries. And here's a plot of this low-pass prototype. It's low-pass because the passband is on the left here. It's at low frequencies, and you notice it has the 1 dB ripple. The red line is 1 dB per division. And then this dot is located at the cutoff frequency, which is at the ripple bandwidth, and that's typically what's done for Chebyshev filters rather than 3 dB down. And then there's a transition band, and then there's a stop band, which is where your specification applies. And prototypes are available with various response shapes, and each is well suited for a specific application. And they used to have books, now they have computer programs that generate these things. Here's a few of the types. Butterworth, it's a maximally flat passband, which I guess you could, it essentially it slopes downhill at all frequencies up toward the stop band. The Chebyshev has passband amplitude ripple, which you saw in the previous example, and the ripple is flat on the lossless filters, and the transition band is steeper than Butterworth. And then there's Gaussian, which has a rounded amplitude, and it has also a rounded time delay response. And these are what you would use for data filters. They're much better for data filters than these things. They don't ring, they don't have overshoot, and that's why they're good for data filtering. You don't get intersymbol interference. And then there's also ones called equal element. These have a steeper transition band than Chebyshev, and they're typically used for pre-selectors where the passband is really very small and right at the center of the frequency of interest. And you can see that in the next example that the passband is not well controlled, but there is a good portion of it right in the center. And then there's also Bessel filters, which are similar to Gaussian, but they have flat time delay. And then there's elliptic filters, which have very steep transition band and actually a lumpy stop band attenuation. Here's a comparison of the attenuation where all these things normalize to the same cutoff frequency. This is 100 megahertz. The markers on the Butterworth filter at 200 megahertz. The Chevy Chef filter, there's the old Butterworth number. The Chevy Chef with the same number of parts beats the attenuation of the Butterworth, but you end up with a ripply passband instead of a pretty flat one. And then here again is the Chevy Chef compared to this one, which is an equal element filter. Now notice the equal element filter has this really ratty looking passband, but typically you have the usable part is here, and you would never attempt to put a signal through this region because it's completely uncontrolled. No guarantee what you're going to get with that. And here's an elliptic filter. Now, elliptics also have a ripply passband that's flat, but they also have the ripply stop band. And you can see that the elliptic filter beats all of them. It has much more attenuation, but it also has more parts. It's a different schematic. And you can get the attenuation in the stop band to be arbitrarily large, but you end up giving up more. You get more ripple if you force this attenuation lower or farther down here. You end up with more ripple. You're wondering, where do we get the prototypes? Well, it turns out for Chevy Chef and Butterworth and Equal Element, it's very simple. This is a formula that generates Butterworth low-pass prototypes. This end here is the load resistor, 1 ohm. The first element is 1 farad. The middle element's 2 whatevers, farads or henries, and 1 farad again. And then the source resistance is 1 ohm. And this formula will produce a variable size array of element values. And here is the Butterworth prototype for 3, n equals 3. It's called an LCL because it's L, C, and L as you go through the circuit. And the dual circuit has the same frequency response. It's kind of amazing to me that that's actually how it works. But oh yeah, the input coil on this circuit here, this is the low pass, creates a high impedance stop band. So if you look at the impedance in here at high frequencies, it's on the rise as you go up in frequency. And sometimes sources, if their transmitters are not happy with a decreasing impedance or an increasing, you have to kind of pay attention to that if you're designing a filter to put on some kind of a transmitter. Here's the dual of that filter. It has the same frequency response, and it's got the same element values, 1, 2, and 1, with the 1 ohm source and load. Seems kind of amazing, but that's the way it works. And then here's a handy formula that will tell you what value of N to use. It will prevent you from getting too many elements in your filter or not enough. It's pretty useful. I don't think anybody uses it much, but if you don't know where to guess for N, that's a good way to get it. Here's the formula for the Chevy Chef prototype values, and again it produces a vector of part values for the prototype, 1 ohm source and 1 ohm load for odd values of N, and even values the source and load are not equal. And it also has a corresponding formula for estimating the value of N so that you don't over design your filter. And then here's for equal element, and I'm not sure how they get these values, but they're constant. Every element in the filter has the same value. So for N equals 3, you make all the elements equal to 1.52, and the terminations are 1 ohm. And this will produce a 3 dB down response at 1 radian per second. And here's a picture of that filter in the low-pass prototype form. Notice all the parts are the same value. Now, in order to get these low-pass prototypes to do something useful, you have to scale the frequency and impedance. And the design procedure is find a suitable prototype and then scale the frequency and impedance to what you want. And here is the frequency scaling and impedance scaling formula for low pass, I guess for low pass and high pass. And in this case, the GP is the value of the element from your low pass prototype, the cutoff frequency of the final filter, and the load resistance of the final filter. And the coil's the same sort of thing, it's just a slightly different formula here. You wonder, how does this actually work? Well, the impedance of the coils are generally described by this 2 pi FL, and the capacitors are 1 over 2 pi FC. The frequency scaling works because you can multiply F by a number, and then you have to divide C by the number, and you end up with the same product. The product does not change if you do that on both parts. So products FL and FC stay the same, ZL and ZC don't change, and the filter continues to work just like it did as a low-pass prototype. And then impedance scaling is slightly different. This depends on Ohm's law. You multiply the resistors and coil values by the desired impedance, which will be your 50 ohm load. That's the number you use. And you divide the capacitors by the same number, the 50 ohms. And the result is that the part values go up in value. I should say the ZL and the ZC and the resistors go up in value. And the circuit voltages are unchanged, and the circuit currents then become divided by the multiplying factor. So the filter continues to work as it did before. It's just got higher impedance. And here's a design example. This one, I wanted to pass 0 to 30 megahertz and get 20 dB of reduction of the third harmonic at 90 and make it be in a 50 ohm system. So I chose a N equals 3 min loss equal element filter. There's no formula available for N. I just arbitrarily picked that. And you have to examine the prototype and make sure that the attenuation you get at 3 times the cutoff frequency is what you want. In this case here, this is the prototype response. I'd like to position my 30 megahertz right here. So this is the frequency that the filter is designed for. So if I multiply that by 3, I don't reach I'm going to end up having the 30 megahertz be 3 dB down, and I really don't want that. So I have to multiply it by an additional factor to take into account this frequency of 0.7, where I want my actual cutoff to be. So I multiply again by 1 over 0.7 and add that, or multiply that times the scale factor. So the scale factor for the 3 dB cutoff becomes 30, which is the one I want, plus this 0.7 thing, or divided by this 0.7. So I have to scale the 3 dB cutoff up to 42.9 megahertz. And I apply those two formulas, GP, 2 pi FCRL. There's the numbers. There's the cutoff frequency from here. And you end up with 113 picofarads, 282 nanohenries, and there's the filter. And here's a plot of the filter in the end user frequency domain. Notice at 30 megahertz here, it's right at the peak where I wanted that. And at 90 megahertz, it's 23 dBs down, which beats the spec. So that's a brief design example of how to get a filter to do what you want. And I think that's the last slide. Yep. That's it.